Hello, this is Math 2270 from the College of DuPage for summer of 2020. And today's topic in this lecture is the Riccati equation. The Riccati equation is a very important application, and I pose this one for your consideration. There's a whole branch of study. Control theory is the branch of mathematics and engineering which defines conditions needed for a system to maintain a controlled output in the face of input variations. Classically developed for automation and robotics, as principally electrical and mechanical engineering, control theory has since been applied to regulatory processes in physiology, genomics, and sociology. An optimal controlled for a linear regulator is a controlled function u hat that looks like this, that minimizes the cost function c of u over all possible trajectories u. And its corresponding solution is called the optimal trajectory. Now this is a research paper that was published by some electrical engineers in the 2018 time frame, and their big theorem was if there exists a solution of the matrix Riccati differential equation, and we will discuss matrix differential equations later, but this is the Riccati equation, and they tell you what all these Q's and R's, A's and B's and S's are, then an unique optimal controlled and trajectory exists on 0 to t. Look, it's an existence theorem. So this is very active even in the 2020 time frame. Now, going all the way back to the beginning, Riccati lived during the Renaissance, and he was a Renaissance man in every sense of the word. He was an aristocrat, but his father was in fact royalty. His father was a count. And he had a large estate that he managed. He also served as the mayor of the town for many years, and he was widely respected. And a Renaissance man means he was interested in many things. He had far-reaching interests ranging from mathematics to poetry, physics to religion, and so on and so forth. He studied law rather than mathematics, but he had some encounters with Nicholas Bernoulli, and his students later had encounters with the great Daniel Bernoulli. This is a quote from him. I think it's inspiring. I do not want to claim that every topic should be probed in detail. Following one's own talent and inclination, one should select at least one topic and study it in depth. In the others, one should follow the example of the bee, which sucks a drop of nectar from each flower. Okay, so here is what the general Riccati equation is. And you see it differs from the Bernoulli equation primarily because there's a thing sitting on here that's called the c of x. And so that's a difference between it and a Riccati equation. And it's used in many different areas of mathematics. It talks about some of them here. In many applied problems, I talked about control theory a little bit. Now, we can solve the Riccati equation with the help of the following theorem. If a particular solution, y sub 1, of a Riccati equation is known, the general solution of the equation is given by y equals the particular solution plus u. And so if we find out what u is, then we can find out what y is, and we'll be good to go. Now, the concept that Riccati introduced was indeed substituting the solution, this, into the Riccati equation. What happens is we get this and this, but now note that the underscored part, this thing, is exactly equal to those because it is a solution. That means you've effectively, when you subtract that from both sides, you effectively eliminate the c of x, and you've turned this into a Bernoulli equation, which engineers have to solve. But a mathematician says, oh, I've changed the Riccati equation into a Bernoulli equation, and I have proven my theorem. So here's an example. You know what to do. Let's see how you did. Well, this really, since c of x is simply a constant, and in fact a and b are constants here as well, the functions of x, this can be separation of variables. This is a good review, and you end up with this once you've separated the variables. And now you can integrate both sides by completing the square. So we complete the square in the denominator, and we have this. Integrating both sides, we get this. And simplifying just a bit, we get this expression. Now, here's another, because that was all I asked you to do, but now I ask you to solve this differential equation, subject to this initial conditions, and find the interval of validity. You know what to do. Let's see how you did. Well, we knew from the previous problem this was the solution that we had, but now we have to solve explicitly for y. So we work through and we solve explicitly for y. Now, this is a good place here to apply the initial condition that I have. So if we apply the initial condition, what we get is this, which tells us that c is this. And solving this all for y, I get this. So that is the explicit solution. And then we can realize that the domain of the tangent function then is going to be from minus pi over 2 to pi over 2. So we solve that and we find that x has to be between these values. So these are the set of solutions that we have to the differential equation, but this is the one that is the solution to our initial value problem. Now here's another example. You want to solve this. This is a different, less simple Riccati equation because c of x is not equal to a constant. You know what to do. And in fact, why don't you be doing that while I go on to section 10.1. So I will see you there.